the organizer for giving me the opportunity to talk. And thank you for being in that room at this moment I give my talk. It's very nice of you. I'm working at the university close by, and I am looking at, and my work is looking at fats and proteins. So I'm doing biology, which is looking at fat and proteins and sugar and water, but biology happens at various scales. It happens at the scales of ecosystems, organisms, tissues, cell, molecule, atoms. What I'm interested in are interaction between molecules. And I want these interactions at the resolution of the atom, or close to the resolution of the atom. And we can get experimental data about that. But these data are limited and difficult to interpret. So if we want to look at what happens at these scales and at time scales that are actually quite short, we can simulate these molecules. And the simulation technique I'm using is called molecular dynamics. Like most physics models, we assume that an atom is a sphere in vacuum, and we apply Newton's equation of motion on these spheres in vacuum. This says that the force is equal to the mass times the acceleration. So if we know what we're simulating, we know the mass of all the atoms, and if we can calculate the force that applies on an atom, we can calculate its acceleration. If we can calculate its acceleration, we can get a velocity. If we can get a velocity, we can get the new position of the atom. Doing that over and over again, we can see the molecule move. And we can calculate the force. So this is part of a model. This is one way of calculating part of the force that applies on an atom. The only thing that matters here is that this force only depends on the vector between two atoms and some parameters that tells what atom types we are looking at. And I've been told to show code. So to run molecular dynamic simulations, we need initial positions and initial velocities. So here I have atoms that I put on a grid with random velocities. I need a way to calculate the force. So this is just the implementation of the formula I showed before. So the first function calculates the vector between each pair of atoms, and the second function calculates the force between each pair of atoms. And I need to be able to use this force to update the coordinates. So I first calculate the force. Because I know the mass, I can calculate the acceleration. And from the acceleration, I can get the velocities and the position and update the plot. And obviously, it does not work. Well, let's hope for the best. No, only the division by 0. OK. You should have seen a beautiful gas moving. And this was crude MD, crude molecular dynamics simulation. It was only in 2 dimensions with only a very small portion of the force. If we add a spatial dimension, and if we add how to calculate the force that happens when you have charges, when you have atoms that are bonded together, then you can simulate systems like this one that are hopefully biologically relevant, with a protein in a lipid membrane, so in fats, alongside nanoparticles, all of this in water. And the point of this simulation was that this protein, we knew experimentally that it was blocked by these nanoparticles, but we could not see how it would happen. Thanks to this simulation and others like it, we can see that the nanoparticles enters into the membrane, sticks to the protein, and restrain its motion. So we gain insight on this process. But I'm not here to talk about molecular dynamics, not the nitty-gritty details of it, at least. I would like to show you how Python is relevant in that context. And I cannot talk about everything there is to say in that field of research, but I can describe my workflow. Before we run a simulation, or before I run a simulation, I need to prepare it. Then only I can run the simulation. I can analyze the simulation and visualize it. And I do that in a Jupyter notebook. And hopefully, and I loop over all of this, and hopefully at some point I get enough result to write a paper. I'm not going to talk about the paper part at all. I feel the deception. I'm not going to talk about the simulation itself either, but I will mostly talk about the part in the red rectangle. But I will start with just a few words about what it means to prepare a simulation. So the simulation is run, in my case, on a software that somebody else wrote, and that has been optimized for years to exploit every little bit of performances the computing cluster can provide. But this simulation engine needs to know what is in the simulation. So it needs a topology. Say, I have these atoms, and they are connected this way. It also needs to know where these atoms are. What are their initial coordinates? And this is ideally taken from using as many experimental data as possible. It needs to know some parameters. What is the temperature? What is the pressure? What are the algorithms that we're going to use? All these inputs are text files. So to prepare them, at least I use a bunch of ad hoc Bash and Python scripts. And once I have these files, I send them on the cluster to the simulation engine, and I get a trajectory. A trajectory is the collection of the coordinates of all the atoms at all the time steps. When I have this movie here, each frame is a time step, and for each frame I have the coordinates of each atom. This is the trajectory. And this is what I want to analyze. So I'm using one simulation engine, but there's plenty of them. Each of them is specialized in something, or is there for historical reasons, or personal preferences. And obviously, each of these simulations engines uses different formats for the initial coordinates. And while some of the informations are in these file formats, some other are in other file formats. And the simulation engine output a trajectory, but this trajectory the file format of this trajectory, of course, depends on the simulation engine. When I write my analysis tool, I could try to parse the files of my simulation engine, but first of all, I do not want to write a parser for that. And I do not want my analysis tool to be limited to only the simulation done with this simulation engine, hoping that the user used these file formats. Because the analysis tool I write, I want to be able to share it with others. I want to be able to use it on trajectories, on simulations run by others. So this is one of the places where Python is really, really useful, because we can have libraries that will abstract all of this mess and give me access only to the information I need. You can get that in a field that has that many file formats. There are many libraries to do that. The only one I'm going to talk about is MDAnalysis. And MDAnalysis reads trajectory and lets you access them, regardless of the initial format. The core object of MDAnalysis is the universe. You give it the topology, you give it the trajectory. You hope that the formats are handled, but most are. And this universe gives you access to the data you need. And most of this data that is in the file are atoms. And you can access these atoms through the very imaginative name atoms. And you get a group of atoms, an atom group, the element of which are atoms. And each atom has attributes attached to it. Each atom has a name, each atom has a mass, each atom has a charge, an element. And you can access this on a position, and you can access these properties, these attributes, through the atom group. Each of these attributes is an NumPy array with the value for each atom. And this is very important that these are NumPy arrays, because then we can rely on the whole Python scientific stack that already exists, NumPy, SciPy, all of these things. You really want to work on all the atoms of your simulations at the same time, so you can select some. And here we try to stick as much as possible to what is done in the Python scientific stack, so you can access your atoms the same way as you would access data in an NumPy array. So you can slice them, you can slice them, it's what I do here. You can index them, give a list of indices. You can create masks and access your atom using a mask. Here, for this specific example, each atom has an attribute called resname, and when you have a water molecule, all the atoms of the water molecule have, in this simulation, the resname set to sol. So here so universe.atoms.resname is an NumPy array that has the resname for each atom, and here I get a mask with true for all the atoms that do not have sol as a resname. But you can also use some more semantic approach to access your atoms, and we have an MDAnalysis has a selection syntax and a bunch of methods that will output atom groups for specific cases. But a trajectory is not only a set of atoms. It is a set of atoms that moves in time. To access the time component of the trajectory, well, we have this trajectory attribute. And this trajectory attribute can be iterated on, it can be sliced. And here, for instance, I print the coordinates of the first atom of my trajectory during the 10 first time step of the simulation. And you would notice that when accessing the position of the atom, I do not refer to the time. I do not refer to the time step that I get from the trajectory. And this is because the atom groups are always reflecting the current state of the trajectory. So I can print the position of the atom, move somewhere else, move at another time of the trajectory, and if I print again the position, I get the current position of the atom. Thanks to all these, thanks to these tools, I can write a specific analysis of my trajectory. I can calculate what is the distance between my nanoparticle and my protein, or how deep in my membrane my nanoparticle is. But a lot of analyses are very common, and we are repeating them over and over again. So MDAnalysis comes with some common analysis already baked in. And we try to have, so here, for instance, I calculate the root mean square deviation. And I can, oh, this is where the simulation was. And I can access and plot the data and hopefully get insights. And I'm not going to go through all the analyses that are available in the library, but there's a few of them. And we try to have, well, MDAnalysis try to have them fitting the same patterns, the same interface as much as possible, and to have the interface being as little concern for the user and for the developers. Okay, but a nice plot is not as nice as the movie I showed at the beginning. I have the coordinates of the atoms. I want to see my molecule. I want to see my molecule moving. There are a lot of tools that allow us to do that. Most of them are desktop softwares. Most of them have a Python interface. Some of them are even written in Python. But I want to see my molecules in my Jupyter notebook. Here comes NGLView. And NGLView makes the interface between my Jupyter notebook and a JavaScript applet called NGL. So I loaded my trajectory before. I can now ask NGLView to display it. I can tell NGLView how to display my view, and I can display a 3D view of my interactive 3D view of my molecule. And this view, and I can see it move. I can visualize my simulation. And not only can I visualize my simulation, but I can control it programmatically. For instance, I can move at a different frame. Or I could choose how to display the molecule. And because it is interactive, I can plug this 3D view with any other interactive part of that I can have in a Jupyter notebook. For instance, here I have a matplotlib plot that is interactive, and when I click on it, I update the 3D view above, so I can see what is the state of my simulation when I have this specific value in my analysis. I can plug it to matplotlib plot, but I can also plug it to IPython widgets. And NGLView is only related to MDAnalysis in the sense that it provides a binding, but they are binding for other libraries as well. So far, everything I showed assumed that I have one simulation. But for every property that I want to analyze, I actually need to run multiple replicas of the same simulation to have sampling, and I need to change parameters to see what is the effect of the parameter. So very fast, my file system is a mess. This is an extract of a cleaned up version, because I was too ashamed of the real state of the directory. So I have multiple setup with different parameters. If for each setup I have multiple replicas of the simulation. And, well, the parameters, they are in the name of the directory, or maybe in a text file somewhere. This is not sustainable. If my file system is a mess like that, I need to be able to find what is the simulation that I ran with that model at that temperature. And this is where datatrend helps. Datatrend allows to attach metadata to directories in a persistent way. The core object is the trend. Code like that, because in Dungeons and Dragons it is a talking tree. I can attach a trend to a directory, and then I can add tags or other data. And this is persistent. If I recreate a trend in the same directory, I get the same data. I can access the data again. These data are saved in a JSON file, which limits what I can store in my trend. So there is an extension to datatrend that is called datatrend.data that allows to store NumPy arrays and pandas data frames as HDF5 files, or any object that you can pickle as a pickle. So you can have metadata and the result of your analysis attached to a simulation, which is already quite neat. But where it becomes interesting, really, is when you aggregate all of that. And you can create a collection of trends and get a bundle. One way of doing that is to discover all the trends that are available under a given directory. And from a bundle, I can access an aggregate view of all my tags, of all my categories, of all my data. I can output a pandas data frame from all the pandas data frame. And I can select only parts, only some trends from my bundle. For instance, here I want to get only the trends that have the tag aggregates attached to them. So this produces a mask, and this selects using the mask. And I went a bit fast, but the first trend I showed you, in the wrapper view, you had trend written. And here it's sim, because this is a specialized trend. You can extend that trend ad nauseam, and you can have specialized trends that knows about what kind of data you're working with. And MD synthesis is an extension that gives me access to MDAnalysis, to the knowledge of MDAnalysis on my data. So because I use MD synthesis, I can attach and retrieve universes from MDAnalysis. I can access how this universe has been created. I can access different selections from my simulation. So even if my simulations are heterogeneous, I can have an homogeneous interface to them. So before I conclude, All the tools I mentioned are open source and welcome contributions. I am only involved in the development of MDAnalysis, not NGLView and not datatrend, because they are already great without me. I do not expect you to, I expect that most of you will not use the library I showed. But what you can get from it is that, well, you know already that Python is awesome. If you did not know that Jupyter was awesome, it's really time to look at it. And each field builds tool on top of the stacks of its field. And I hope that the tools I showed you gave you ideas for your own field. Thank you.
Thank you. There's some time for questions, everybody. 1, 2. So there's no questions? Oh, there's one in the back.
Hi, sorry, I came in a bit late, so maybe I missed it. But in MD, trajectories can become very, very large very quickly because you have millions of time steps over hundreds of thousands of particles.
Yes.
So how does MDAnalysis deal with that? Does it load it all in memory, or?
No, it loads only one frame at a time, which avoids breaking your computer apart when you start analyzing a proper simulation. So you have, so your current state is always a single frame, and you can access every information about the current frame. We do have mechanism if you have simulation small enough that allows to load all of it in memory. And if your simulation is small enough and you can actually fit it in memory, then you can expect increase in performances.
And is this loading on demand really that transferable between the different file formats of all the different MD engines?
Sorry, I did not hear.
So you load every frame
Yes.
on the fly, really, from disk?
Yes.
So is this transferable between all the file formats that all the different simulation engines provide? So
MDAnalysis can read a trajectory from a file and write a trajectory to another format. Assuming that all the data required from the output formats are provided by the input one, or that you can add them to the, if you read your trajectory in a format that does not have the charge of the atoms, and you want to write a file that requires the charge of the atom, well, except if you enter the charges yourself afterward, you cannot write it, obviously. But except for that, it works in most cases.
Any more questions? Yes.
Can you also render movies with these tools, or do you need to move to something else?
I think NGLView can render movies. I never did it, so I don't know the syntax, but I'm almost sure, I know for sure it can render images, and I think it can render movies.
Maybe one final question. Also, I'd like to thank Jonathan for a nice talk. Please give him a warm hand. Thank you. Thank you very much.